Okay, so this is the first topic we're going to cover in the course, and it's really a very simple introduction to sets. And the point of this topic is not to go into detail here, it really is just to make sure that we all understand common notation and common ideas about sets. Okay, we all learn about sets in school, but we all learn things maybe slightly differently, so I just want to make sure that everything is kind of homogeneous. Okay, so let's get started. Really what we're doing here is we just need some basic tools to understand collections of objects. And the definition we're going to give for this collection of objects, namely a set, is going to be a very, very informal definition. So a set here, notice I'm highlighting the important terms here. The set here is just a collection of objects. And the objects in this set are referred to as elements or members of that set. Now, we give a very informal definition here because we just want something simple and intuitive so that we can get on with things. But it also turns out that giving a rigorous definition is actually way harder than what we need. Okay? So a rigorous definition of what a set actually is turns out to be a very difficult thing. So let's just go with this very informal definition here, namely a set is a collection of objects. Now notice here, as part of my writing things up, I'm going to make sure that the definition stands out very nicely here. What we have to do is we have to think of the person who's reading our material. So I'm going to give this definition, I'm going to put it in a nice big box, I'm going to highlight the important terms. This is something we'll do again and again. Okay? So we have to think about the person who's looking at the material we're discussing. So a quick aside on conventions in notation, mathematics has a very large number of convention traditions. And in general, these are not firm rules, but they're there to make it easier for the person who's reading the mathematics that we're doing, make it easier for them to understand. And this is something we really do have to keep in our mind when we do mathematics, especially for this course and what happens after this course. We need to make it easy for the reader to understand what we're doing, what we're saying, what we're discussing. So one thing that happens, it's a fairly standard notation, is we use capital letters for sets. Okay, so we'll use capital A, B, C, X, Y to be sets, and we'll use lowercase letters to denote their elements, A, B, C, X, Y. Okay, and one thing we can do is if we're discussing multiple sets and elements from those sets, we can talk about little a coming from big A, little b coming from big B, and so forth. This just helps the reader keep track of what's happening. Similarly, we'll typically use the lowercase letters I, J, K, L, M, N to denote integers, whole numbers, and we'll typically use X, Y, Z, W to denote real numbers. Okay, now these are not hard and fast rules, they're just conventions that make it easier for the reader to see what's happening. So if we see I, we think, oh, it's an integer, probably a small integer or a counter, something. If we see X, we probably think it's a real number. And you've already seen this with things in calculus where you have f of x is always a function that takes a real number x. And we may have seen g of x. And y is equal to f of x. These are just standard conventions that we'll use again and again. Okay, these are not hard and fast rules, but they're very helpful to help people understand what's happening. Now, a set is a very simple mathematical object. In fact, the only thing we can do with a set is ask the question, is this object in the set? And the set can only answer yes or no. It can't tell us this object is in the set 3 times or it's the 17th thing in the set. It can only tell us if an object is in the set or not. Okay, so it's a very, very simple mathematical object. And so, for example, if we let capital E be the set of all positive even numbers, then the number 4 is in E because it's even, it's 2 times 2, but 3 is not in E because it can't be written as 2 times another integer. And this set E doesn't know anything else about 3 and 4. It doesn't know that 3 is prime, it doesn't know that 4 is, say, the second thing in that set. That doesn't even make sense. So the set is a very, very simple object. So again, some notation. Mathematicians use a lot of notation, a lot of shorthand, so we should try to keep ourselves using standard notation to keep things easy for the person reading it. If A is in an element of the set A, we write A and this symbol here meaning is an element of A. If B is not an element of set B, we write B, the same symbol now with just a stroke through it, B. So we should think of this symbol as shorthand for is an element of. Okay, so this is really a little sentence here, namely A is an element of big A. And this is again shorthand for a sentence, B is not an element of big B. And something to be aware of, a lot of you may have used this lowercase epsilon as an element of. Please don't do that. This is not the same as this. This is an epsilon, this is an element of. So please stick to standard notation. So if we go back to this set E, we know that, for example, we can write 4 is in E and 3 is not in E. On the other hand, the statement 4 epsilon capital E is, well, as a mathematician, we would read this as it's a product of three things, 4, epsilon, and the set E, which doesn't make sense. So this is garbage. So please stick to standard notation. Use this symbol to denote is an element of, and this symbol here to denote epsilon, if we ever come to that. So now, when we define a set, it's important that we make our definitions very clear. So, for example, let A be the set of even integers between 1 and 13. It's nice and clear. If we, for example, let B be the set of tall people at UBC, that's not clear. What is tall? Who's at UBC? Does that mean the Vancouver campus, the Okanagan campus? Is it today, etc., etc.? So we have to make sure that things are very, very clear when we define or describe a set. So if there's only a few elements in the set, then the easiest way to do it is just to list out the elements. So for example, the set C here is just going to be the set of numbers 1, 2, 3, 4. Okay? Nice and clear. If we want to see if something's in the set, we can just look at the list and see if it's there or not. If we do this, then because a set only cares about membership, it only cares whether an object is in the set or not, the order in which we write out this list doesn't matter. So putting things in order, 1, 2, 3, 4 is the same as 2, 3, 1, 4, 4, 1, 2, 3. We can still only ask the question, is this in the set or not? And we're just looking at the list. Okay, so the order in which we write things doesn't matter. Similarly, repetition doesn't matter. So the set 1, 2, 3, 4 is the same as this set here, because this set here, despite the repetition, still only contains 1, 2, 3, and 4. Okay, but because order doesn't matter and repetition doesn't matter, we should be nice to the person who's reading stuff and make sure we just put things in order and don't repeat anything. Okay, this is just keeping things easy for the reader. Now, that works quite well when we have a very small set, but if we have a larger set, then we've got to do things a little bit more creatively. And one of the things that we typically do is we use these 3 dots, namely an ellipsis, as shorthand for skipped elements, okay? That's sort of telling the reader, hey, you get the idea of what's happening here. So for example, the set C here, we'll write as 1, 2, 3, 4, ... up to 40. And what we're telling the reader here is that this is the set of all positive integers between 1 and 40 inclusive. Okay, so it's pretty clear. The set A being 1, 4, 9, 16, ... This is the set of all positive square integers. Okay, again, this should be fairly clear, and maybe we're expecting the reader to understand this by context. Okay? And speaking of which, we've got to be careful. We've got to make sure when we do use this ... this ellipsis to describe a set, that it's very clear what's happening. So, for example, if we take this set here, B being the set 3, 5, 7, what is this set? Is this the set of all odd primes? Is this set for all odd numbers bigger than 1? Is this the set of prime numbers that are 1 less than a power of 2, or what? Okay, so this is a bad example. Okay, we don't want to write something like this. So please don't do something like this. Make sure your definitions are precise. If the definition is vague, then it's not really a set. Okay, so you have to help your reader when you're doing this. You have to assume that they're going to that you've put enough on the page. Don't assume they will get what you mean. Okay, so be careful when you're describing a larger set. Now, let's define some important sets. Perhaps the most important set is the empty set. So the empty set is the set that contains no elements. It's typically denoted by this circle with a stroke through it, so just like this, and we define it to be the set that contains no elements. So that means for any object x, we know that x isn't in this set. So no matter what we choose, it's not in the set. So now, sometimes people get confused between the empty set and nothing. So the empty set really is like an empty bag. It's not nothing. Okay? So it's a bag with nothing in it. So if we keep going here, the set A, which we define to be the set with the empty set inside it, it's not empty. It contains one element, namely it contains the empty set. So the empty set here is an element of A. The set B here I've written as this mess here, and it contains two elements because that is in B, and the set containing the empty set is in B. Okay, so that contains two elements. Okay, so playing around with the empty set can sometimes be a bit confusing, but it is really the most important set. Okay. So now, for larger and more complicated sets, it becomes easier to define them by a rule. Rather than writing things out with or without this ... we define them using a rule. So for example, the set of all even numbers we can write as x so that x is even inside the brace. So we have a rule here that tells us whether something's in the set or not. This so that can be simplified or contracted to just st, or a vertical bar, or a colon. You'll see all of these three things. Now, this sort of notation where we have a set, let's see if I can get this to delete. This set defined by an expression, colon, a rule, is called set builder notation. It tells us how to build the set. Okay? So for example, the set A of n squared such that n is a whole number. Notice what I did there. N squared so that n squared is a whole number. So I'm reading that vertical bar or the st or the colon to mean so that. So it's kind of a sentence here. N squared so that n is a whole number is just the set 0, 1, 4, 9, 36, etc., etc. Ooh, if I skip things in here, I've skipped things in here. Okay, so I've written this pretty badly. Maybe I'd better fix this. Okay, 0, 1, 4, 9, 16, 25, and so forth. We can write B here is an elements of A that are less than 12. So it's just going to be the numbers 0, 1, 4, and 9. We can write A so that A plus 1 is a prime. Well, we'll have to think about this a bit. 2 is a prime, 5 is a prime, 17 is a prime, and so forth. So the important rule here is that you're clear. Help the reader. Help the person that's reading what you're writing down, even if that's just yourself. Okay, so it's really, thinking about the reader is really just a mnemonic device or a simple way of checking, is what I'm writing down clear enough? So let's write down some other important sets. We have the natural numbers, or the positive integers, so that it's just 1, 2, 3, 4, and so forth. These are the ones that we encounter when we're very, very young. And it's important to note here that 0 is not in the natural numbers. There's a long discussion about why that's the case. The integers are all numbers, positive, negative, or 0. So these are the superset of the integers. Rational numbers, you probably just know as fractions, are all numbers a divided by b, so that a is any integer and b is a natural number, because we can't divide by 0 and it makes sense to keep negative in one place. We have r being the real numbers, okay, so all numbers that we're used to dealing with, and we denote all of these sets using blackboard bold letters. Okay, so it's important that we use this strange sort of double-stroked letters here to denote our sets. Okay, or to denote these important sets of numbers. So please do use correct notation. Capital N is not the same as blackboard bold N. Capital Z is not the same as blackboard bold Z. We might also see from time to time the set of irrational numbers being written with this blackboard bold I. So these are a set of real numbers that are not rational. And indeed, in this course, we'll prove the fact that root 2 is an irrational number. We can't write it as a fraction. One last thing before we get on with other topics. So we talk about cardinality, which will be a major topic near the end of this course. We use putting these vertical bars on either side of a set to denote the number of elements in S. And the number of elements is called the cardinality of the set. So for example, the cardinality of the empty set is 0. The cardinality of this set here is just 3. And the cardinality of this set here, because it contains the empty set and another set, so I've got one set here, another set there, so it contains only 2 elements. So for finite sets, this is pretty straightforward. But with infinite sets, the notion of cardinality becomes very strange. So for example, we will prove in this course that the number of natural numbers is the same as the number of integers. And this feels kind of weird because there are kind of twice as many things in there as there are in there. But we'll prove this. We'll also prove that the rational numbers are the same size as these two other sets. And importantly, we'll also prove that the set of integers is smaller than the set of real numbers. And so we'll prove all of these things in this course. And that's where I'm going to stop this first topic. Thank you.